It's good, you can start.
Okay, thanks everybody for coming and listening again. So we'll continue where we left off yesterday. Remember, we introduced this stationary partition function, originally defined by O'Connell-Lignor, and it had this interpretation of an ensemble average over averages of upright paths, so semi-discrete paths that jump at times labeled by S. Okay, so here's the definition again. At each level, we accumulate a Brownian increment, but there's this initial level before the first jump time, S0, that has a special role. There's a special weight, theta times S0, and there's a Brownian motion, B0, S0, associated to that level. And we showed part of the proof of how you get the upper bound, at least for the variance, provided you're in this characteristic direction. So this characteristic direction is this condition on the parameters n, theta, and t. So t is the final time here, the time where we stop our paths at level n. N is the number of levels, the number of Brownian motions. And we gave a proof, or we gave an idea of how to prove this variance bound, assuming a few things. In particular, one assumption that we made is one that we'll start with by discussing today. But let me first remind you what was special, what's stationary about this situation. It's that you could write log of z and t, you could write it as a sum of increments. Here the increments rj, remember, are the differences between the partition functions for different sizes. So log of zj minus log of zj minus 1 plus a Brownian motion minus theta t. The RJs among themselves are independent, they're IID, and we know their distribution, in fact, but they depend on the Brownian motion, and the interaction between that Brownian motion on the boundary and the RJs is what gives us these special fluctuations. And that was, we could see that through this formula, this exact formula of Sepelainen and Vackel, this exact formula for the variance in terms of an average of the quenched expectation of S0 plus, the positive part of the first time we jump in the system. So that time could be negative, right? If you go back to the partition function here, we start at minus infinity, but in fact, it won't be too far from 0. And we see here that the variance can be bounded in terms of the positive part of that jump. And the first step in getting this n to the 2/3 bound was to replace or to bound this S0 plus by the expectation of S0 squared. Remember, the reason we wanted to have the quenched expectation of S0 rather than the quenched expectation of S0 plus is that the quenched expectation of S0 was the derivative of the partition function with respect to theta. And so we could use convexity to bring ourselves back to the partition function, the log partition function, and get this closed equation for the variance. We got this equation v, where v is the variance, is bound by n to the 2/3 plus n to the 1/3 times v to the 1/2. From this, we could conclude that v was at most n to the 2/3. But one important step was this step, replacing S0 plus by expectation of S0. And as I said, this is not completely obvious because S0 potentially could be negative. Okay, so it's possible that S0 could be negative. So we have to make sure there's no special cancellation in the quenched expectation that would make it much smaller than S0 plus. So that's what we'll start with today, is comparing the expectation of S0 with the expectation of S0 plus. The plus, remember, is just the positive part. So when I write S0 plus, I mean the max of S0 and 0. So that's equal to S0 whenever S0 is positive, but otherwise it's 0. So of course, S0 can be written as S0 plus minus S0 minus, where you have the negative part, the maximum of minus S0 and 0. So we can write the expectation of S0, the quenched expectation of S0 squared as this sum of squares, two non-negative terms, but then there's this cross term, expectation of S0 plus times expectation of S0 minus. And so what we can say, certainly, is that the quenched expectation of S0 plus is bounded by the quenched expectation of S0, but then we have to make sure that this term here is not very large. And a priori, when we take the expectation, so this is not something that I expect you to know, it's not obvious, but it will turn out that really expectation of SCO plus, when we also take the average over the Brownian motion, it really is of order n to the 2/3. It's not just bounded by that. And similarly, the expectation of S0 minus, the negative part. And so if we don't allow cancellation, if you wish, you're going to have, when we take the Brownian motion average, in addition to the ensemble average, we get n to the 2/3. So the fact that these two quenched expectations, their product is small, it's not too big, it's no bigger than n to the 2/3. Actually, it's no bigger than n. That's not totally obvious because it means that SCO plus and SCO minus, if we fix the Brownian motions, cannot be simultaneously very large. Even though on average, when we average over the Brownian motions, they are both of size n to the 2/3. So my claim here is that this product is of order n, at least at most of order n. Actually, it can be quite a bit smaller, but in expectation, when we average over the Brownian motion, this product is at most of order n. So basically, when we freeze the Brownian motions and we build that ensemble average, remember, whenever I write expectation without this math BB, I mean the ensemble average. I mean, you take the average with respect to the Gibbs measure corresponding to the partition function. So you multiply by this Gibbs weight e to the theta S0 minus B0 S0 plus the rest of the increments of Brownian motions. And then say you're taking the average of a function f, you put f here, you divide the whole thing by the partition function. So this depends on the Brownian motions. It's a quenched measure. It's still a random measure. And what I'm saying here is that even though when we take the average of this with respect to the Brownian motions, SCO plus and SCO minus are both separately of order n to the 2/3, they are not simultaneously very large. Okay? So once you freeze the Brownian motions, either one of them is large and the other is small, or vice versa. Okay, so if you want, you can think about the picture as being as follows. If we take this, the blue here corresponds to the annealed averages. So that means when we average over the Brownian motions. When we average over the Brownian motions, S0 can be within n to the 2/3 on either side. I mean, depending on how we choose n, t, and theta, it could be more likely to be on one side than the other, but it will be in the region of size n to the 2/3 around 0. And it can actually fluctuate on this scale when we allow the Brownian motions to vary. But if we fix the Brownian motions, then S0 will be very close to its, it will be n to the 1/2, so very close. That's relative to, depends on your definition of very close, but it'll be much closer than this n to the 2/3 scale to the expectation. It'll be much closer to the expectation with respect to this quenched measure. Okay, and that's what causes this fact that when we multiply expectation of SCO plus and SCO minus, well, SCO is going to be either very positive most of the time or very negative most of the time. The Brownian motions staying fixed, so they're not going to be simultaneously large. But how do we see this? How do we, prove? This is just me making this claim. How do we see this? Remember, we don't have that many tools. Our main tool is just this invariance, so we can compute expectations of log of Zn and take some derivatives. That's basically the only thing we know how to do. So for this, we'll do a computation and we'll see the things drop out pretty nicely. So let's compute the variance with respect to the Gibbs measure of S0. So how close is S0? If this picture is true, then we should be able to see that the expectation of S0 with respect to the quenched measure is a good measure, is a good approximation of what SCO is typically. So we should compute the variance of SCO with respect to the quenched measure. And let's compare that to the variance of SCO plus or SCO minus with respect to the quenched measure. So let's just expand the square and be careful here about the sign. SCO is equal to SCO plus minus SCO minus. And then when we expand the cross term, we have to remember that SCO plus or SCO and SCO minus have disjoint support. So when we multiply SCO plus with SCO minus, we just get 0. And so expanding that cross term, we are left just with expectation of SCO plus times expectation of SCO minus. That's what we're trying to control, with a minus sign in front. Okay, so that's fortuitous. It's very nice. It will work out in our favor. Okay. Why does it work in our favor? Because this cross term we're just computing, it appears over here in an equation where all the other terms are non-negative. Okay, so that will allow us to give a bound for expectation of SCO plus times expectation of SCO minus in terms of how close all the SCOs, either SCO or SCO plus or SCO minus, are to their quenched expectations. Okay, so the variance of SCO, that's what we computed up here. So let me write it here. The variance of SCO, the quenched variance of SCO, we can rewrite as the quenched variance of SCO plus the quenched variance of SCO minus plus twice the expectation of SCO plus times SCO minus. This because the two minuses, the two red minuses here, cancel. And so we're left with the fact that expectation of SCO plus times expectation of SCO minus is controlled by the variance of SCO, the quenched variance of SCO. Okay, and this term on the left here, expectation of SCO plus times expectation of SCO minus, that's the term that we need to control. That was the missing term we needed to control. That's the one we want to say is not too big if we are to replace SCO plus by just SCO in expectation. Okay, and so we're saying the term we wanted to control is bounded by the variance of SCO. But whenever we don't have pluses, whenever we're just talking about SCO, that's something that we know how to compute because of stationarity. Because the variance of SCO, that's the second cumulant of SCO with respect to the Gibbs measure. And whenever you have a Gibbs measure with a linear term, we used that last time. Whenever you have a Gibbs measure with a linear term, when you differentiate with respect to the parameter in front of that linear term, you get the cumulants. So the variance of SCO, the quenched variance of SCO, is a quantity we can compute by stationarity, at least on average. Okay, so what do I mean by this? Okay, taking expectations in the previous equation, we find that the expectation of SCO times expectation of SCO minus, and take the ensemble, the Brownian motion average, sorry, this is bounded by the expectation of the quenched variance. But now the quenched variance, that's the second cumulant of SCO, but SCO, again, appears linearly. It appears linearly in the Hamiltonian. Right, so Z is e to the theta S0. It's an integral of e to the theta S0 plus something else integrated against ds, integrated ds. So when we differentiate with respect to theta twice, we get exactly the quenched variance. But we can move the second derivative outside of the expectation, and the expectation we know how to compute. That's because we know that log of Z is written as a sum of a Brownian motion plus these IIDs, and these IIDs are explicitly computable. And so in the end, we find that the expectation of the quenched variance is of order n. And correspondingly, the expectation of SCO plus times expectation of SCO minus, then take the average with respect to the Brownian motions, is at most n. So indeed, going back up here, indeed, this is true. It is true that this expectation is of order n. And why did we want to do that? Well, we wanted to do that because this term here is exactly the missing term if we're trying to replace expectation of SCO plus by expectation of SCO squared. Okay. So this order n we can afford because anyway we're trying to because this order n is going to appear under a square root, and anyway we're trying to get a bound of order n to 2/3 in the end. Let me just go back to show you what I mean. Over here we have a square root, so this order n is going to appear under a square root, so it's fine. We can afford this order n error. Okay. Any questions about this? All right. So this is the phenomenon that allows us to make this replacement, S0, because S0 is pretty concentrated, there's no cancellation that could get in our way and make it so that expectation of S0 is somehow much smaller than S0 plus. So the final ingredient to close the proof from last time is this bound for the increments of the variance. How does the variance change when we modify the parameter theta? Here we're going to follow the proof that Zeppelin and Balco use. We'll see next time that there's a different way in the diffusion case to approach this. And there's also another way that's not in our paper that I might be able to show you to show that this is actually the correct order when you modify the argument. But this proof is pretty conceptually easy to understand. So we want to show that when we change the variance, when we change the parameter by h, the variance changes by n times h. So remember what the context is here. Why were we trying to get this? This error is actually one of the two errors that in the end dictated this n to the 2/3 scale, because this error we compare to the error that we get when we shift the parameter, the error in the expectation, and that error, by exact computation, we found was of order n h squared. And by comparing these two errors, by comparing actually the square root of the error in the variance to this cn squared, we found that the right choice of h was n to the minus 1/3, and that's what dictated this n to the 2/3 scale in the end. Okay, so this is a very important fact, but it's also quite easy to prove once we use the Zeppelin and Balco identity. So remember the variance we can write as n times psi1 theta plus h minus t, plus this expectation of the quenched expectation of S0 plus. But now, what is the effect on this quenched expectation of modifying the parameter theta? If we increase the parameter theta, if you think about how theta appears, I mean, I'm going to do this intuitively, but if you think about how the parameter theta appears, increasing theta will make it more likely that S0 is large. Okay, it'll put a larger weight on larger S0. And so increasing theta will make this quenched expectation of S0 plus larger. Okay, it'll push S0 towards positive values, so it'll make S0 plus larger. You can make this precise by differentiating and looking at what you get, differentiating with respect to theta and looking at the quantity that you get. You'll see this quantity as positive. It'll be the covariance between S0 plus and S0. But also intuitively, if we increase the parameter, then this e to the theta S0 is going to push us towards positive values of S0. So increasing theta increases this expectation of theta S0 plus. So when we take the difference of these two terms, we can drop this positive term, the positive term that results from taking the difference between two expectation of e theta plus h minus two expectation of e theta. Okay, so we get this first inequality. We get a lower bound for the difference in the variances. But now this function psi1 is a smooth function. So we can replace this psi1 theta plus h minus psi1 theta by a constant times h, when h is small. Okay, now what about the upper bound? For the upper bound, let's start again from this variance identity. Same thing as before, n times psi1 theta plus h minus t plus twice the expectation theta plus h of S0 plus. Then now let's replace S0 plus by an expectation of S0 and an expectation of S0 minus. Remember, S0 is S0 plus minus S0 minus. We defined S0 minus so that it's a positive quantity, or at least non-negative. But now expectation of S0 without a plus or minus, that's equal to t minus n times psi1 theta plus h. Why is that? Well, remember the expectation of S0 is equal to the derivative of the expectation of log of z, and that derivative is exactly the negative. Is exactly equal to this quantity here. Okay, And so we're left only with this twice expectation of theta plus h S0 minus. But now, by the same reasoning, or by the reverse reasoning that we used before, if you increase the parameter, then you tend to make S0 bigger, so you tend to make S0 minus smaller. So increasing the parameter makes expectation of S0 minus smaller. So we have the reverse inequality that we had before, and so we can also bound the difference of the variances by n times the difference of this psi function, psi1 function, at theta and theta plus h. So for small h, we get n times h as the difference. Okay, so indeed the variance shifts by c times n. Any questions about this? So in summary, what did we do? We combined the stationarity, so this O'Connell-Yor identity, with some arithmetic to obtain, and Gaussian integration by parts to obtain the Cepelin and Valco identity that are, just to be clear, I mean, I'm using their name, but to be clear, they obtained this already 10 years ago. We just give a slightly different proof from what they did. And then we used convexity and this replacement of S0 by S0 plus by S0 to get to a point where we bounded the variance in terms of n to the 2/3 times the variance at different parameters. And then we had to bring ourselves back to the original parameter. That's why we've been doing these computations of what's the shift in the variance, what's the shift in the expectation. And then by optimizing this parameter h, we found this n to the 2/3. And we got this inequality for the variance in terms of itself that forces it to be at most n to the 2/3. Okay. So let's move on to some newer things. This is some work that we did last year with Christian Noah, who was a postdoc at Cornell. He will be an MSRI next year. So with Christian, we looked at the question of higher moments. So we have this nice method, this general almost philosophy, this coupling method, again, that originated with Balázs Kator Cepelinen and was developed in many papers. And it allows us to get bounds on the variance and also the deviation from the straight line, this S0, that are of the correct order. So we only talked about the upper bounds. You can also get lower bounds. But so far, at least until last year, our work with Christian and also some more recent work of Cepelinen and Emrah and Jajingin, the higher moments were not really accessible by this method, but it turns out that you can also use this method to control the higher moments. So when we write that log z bar, so log z centered, is of order n to the 1/3, perhaps at least when we're in a situation where the environment is Gaussian, we would expect that it's of order n to the 1/3, not only at the level of the variance, but also at the level of the higher moments. So if P is even, so maybe here we want to have P even. If P is even, is it the case that log of z bar is of order, log of z bar to the P is of order, is of order n to the 1/3 times P. So in case P is equal to 2, this was what we just proved, n to the 2/3. Of course, if you think about how we did, how we proved the case P is equal to 2, the first step would be, do we have a higher order version of this identity, this variance identity, right? We were working with this identity that related the variance to this more geometric quantity, and then we somehow deal with this geometric quantity. In our case, we related it back to log of z bar. In other methods, you try to get an upper bound for S0 plus either directly or again by relating it to the central moments, by relating it to central moments or the variance of log of z bar. But here we want to study the higher moments. So how do we get started? Remember how we obtained that variance identity? The way we obtained it is starting from this decomposition, this useful decomposition of O'Connell and Yor. The fact that log of z could be written as a sum of IIDs plus a Brownian motion that's correlated with the IIDs. And then we just took variance on both sides, essentially. The problem is that if we immediately take, say, the fourth moment on both sides, we get expressions that are a bit complicated to deal with. So for example, suppose I take the fourth moment, I move R to the left, or I move the Brownian motion to the left, and I take the fourth moment, and then I get something like what I wrote here. This is what I'm now doing. Sorry, I'm not sure what this question means. This is what I'm not doing. Okay, so there was a question. Sorry. Okay. Let me continue, and if there are further questions, I'll address them. Okay, so if we take the fourth power on both sides, if we take the fourth moment on both sides, then we have this expression here. But now let's think about this expression. Let's do some power counting. Let's look at the size of the terms here. We're hoping that log of z bar to the fourth will be of order n times 4/3. But immediately, for example, we have a term here that's 3t squared. Okay, so this term looks like it's going to be too big, so there has to be some cancellation. But even if we look at the other terms, look, for example, at the term over here, this term log of z bar squared times b0t. Now, log of z bar squared, let's assume that somehow by Holder or whatever, we know that for moments that are lower than 4, we know that we're of the correct order. So we'd have log of z bar, which is of order n to the 2/3. Log of z bar is of order n to the 2/3. So squared would give us n to the 1/3. So squared would give us n to the 2/3. But then we have the Brownian motion at time t, which is squared. Okay, so that would be of order t. But t is of order n. So already here, this term looks like it's going to be too big as well. We also need to massage it somehow to find some cancellation. And you can do the same type of power counting for the remaining terms, and you see that this t here in the Brownian motion seems really deadly. Right? The Brownian motions are going to be of order t to the 1/2 when t is large, but t is of order n. Okay, so clearly we want to rewrite this a bit before we can apply an inductive argument. Okay, any questions about this? Inductive on the moments. Yeah, correct. An inductive argument on the moments. Any other? Okay. Oh, I think I understand what the first question is, but I think we'll get to this later. Let me move on. So what we did with Christian is instead of looking at the moments, we use the cumulants. And then when we work with the cumulants, we'll see certain cancellations will be easier to grasp. Okay, so let me just remind you what cumulants are. So the kth cumulant of a random variable is the kth derivative at 0 of the log moment generating function. So the log of the expectation of e to the lambda x. We can also look at joint cumulants. So, and the kth cumulant of x is actually a special case of the joint cumulant. So the joint cumulant of k random variables, x1 to xk, you obtain by taking the same expression, log of the expectation of e to the, but then you take a linear form, sum of psi I xi, and you differentiate once in each of the xi's, and you set xi equal to 0. So here when I write xi underline, I mean the vector xi. So when I differentiate here with respect to xi, I differentiated each of the directions xi1, xi2, up to xk exactly once. So ultimately, we really want to get at the moments. We really want to get at the central moments, but the useful formula that we were able to come up with is expressed in terms of the cumulants. But if you look at the definition of cumulants, or if you've worked with them before, you know that the cumulants can actually be expressed. There's an explicit expression, but for us, the thing that matters is that the cumulants is equal to a sum where one homogeneous term is going to be the kth moment, and then they're not lower order terms, but there are terms that involve sums of products of expectations of x, of different moments of x, of lower order. So here's our replacement. So this is with Nowak. This is with Nowak last year, maybe 2020. Okay, we came up with this formula, which looks very complicated and somewhat hopeless, but as we'll see, we only need certain features, certain qualitative features of this formula to get our machine going. It's a formula for the kth cumulant of log z. And okay, so the kth cumulant of log z is equal to a term of order n times, and the coefficient of that term is psi k minus 1 theta. So psi k here is the kth derivative. So the k minus, the kth derivative of this function psi 0. Remember, psi 0 was gamma prime theta over gamma, the logarithmic derivative of the gamma function. And then we have a term of order t, which only appears when k is equal to 2. And then we have a complicated sum over partitions. And if you have worked with cumulants, you may recognize this type of sum. And what's important here is really the qualitative form of what we're getting. We're getting a sum of products of expectations, of products of partition functions, but the partition functions, the powers that are involved will all be smaller than k. That will be very important, times some Hermite polynomials. So the Hermite polynomials are the orthogonal polynomials with respect to the Gaussian measure. Here, they're Hermite polynomials that are adapted to this Brownian motion with variance t. So they're orthogonal polynomials with respect to a Gaussian measure with variance t, the centered Gaussian measure. The sum over is over partitions of 1 up to k, and b's are blocks of the partitions. And if you want to know exactly what these powers aj and bj are, they're defined there. So ajb is the size of the overlap between the indices 1 up to j. J is always going to be strictly less than k, and the block of the partition, and bj is the complementary size. So it's the size of the block minus aj. Okay, so perhaps later I'll explain how you come up with this formula. It's not too difficult. Essentially, the way that that you get this formula is by applying, instead of taking moments on both sides of this, you take cumulants on both sides. And then the only mystery, I guess, is how do the Hermite polynomials appear? But the reason the Hermite polynomials appear is just because you're taking cumulants. When you take these joint cumulants, you can replace the Brownian motions by Hermite polynomials. That's just because of how Hermite polynomials work. Perhaps I'll explain this if there is time later. For now, let's just start with this formula and see how it. But let me just stop here and see if there are any questions. Any questions? Everything clear so far? Okay, so how can this be useful to us? So remember this cumulant here, the kth cumulant, it starts with its leading term, where it contains what we're really interested in, which is the kth moment. So I see your questions. Sorry, yeah, it is HKT, sorry. Are you asking whether the Hermite polynomial with degree k appears? Well, the Hermite polynomial with degree k can be ignored because the only way that Hermite polynomial with degree k would appear, it would appear alone in an expectation, because k is the largest possible size of any block, but that expectation would be 0 because you would be taking the expectation of a Hermite polynomial of that degree. Does that make sense? So the total degree of AJB plus BJB, that has to be less than k. The Hermite polynomial of degree k does not appear. That one doesn't come up in the formula. Okay, so let's look qualitatively at what we've obtained. We've written the expectation of log of z bar to the k as a sum of products of expectations of log of z bar to some power. And what's important is that all these powers will be less than k, strictly less than k. And also, when we take a product over B, so there are different powers, A, B, B sub B. When we take a product over B, the total homogeneity is equal to K. Okay, but we still have the problem that we discussed before, is that even if we knew that for powers less than K, log of Z bar is of the correct order. Say if we knew that log of Z bar to the AB is of order n to 1/3 times AB, we'd be stuck here because these guys look like they're too large, right? The size of the Hermite polynomial of order L evaluated at B0t is still t to the L over 2, and t is of order n. So the homogeneity doesn't work out here. Like we're not able to do an induction. Okay, so it's not good because t is of order n. So even if we had the best power for lower moments, we still wouldn't get what we want by induction. Starting, say, for example, we know the variances of the correct order. We apply this formula to get an expression for the expectation of log of z bar to the fourth in terms of products of expectation of log of z bar to a power that is less than 4. Even if we knew that all these powers, all these lower powers, their moments are okay, because of these Hermite polynomials, things are still too big. So we need to somehow exploit this, find the cancellation. Just to make sure, things, I'm not talking about something that is magical or like very far from what we've been doing so far. If you remember yesterday, we showed that expectation of B0t is equal to this expectation of S0 plus, and S0 plus ended up being of order n to 2/3. But if instead we looked at this, right? If instead we looked at B0t times log z bar, then we would also get a homogeneity that is not of the right order. We'd get n to the 1/3 for log of z bar, and then here n to the 1/2. So we wouldn't get something correct. So you have to, you have to somehow, you cannot just do Cauchy-Schwarz here. You have to somehow show that there is some cancellation between log of z bar and B0t. So that's what we want to do, just at a higher level than just for degree 2. So we're going to use Gaussian integration by parts again, and that's why the Hermite polynomials are useful. Because if we look at the expectation of log of z bar, or really any function of B0, including the entire path, not just B0t, then we can integrate by parts, and I'm writing here. So the middle term is symbolic. It's a functional derivative of log of z bar with respect to B0 t, and it's the jth derivative because we have the Hermite polynomial of order j. Okay, and now the final term, that's actually correct. It's not symbolic. This will be equal to -1 to the j times the jth cumulant of S0 plus with respect to the quench measure. In case j was equal to 1, we just had B0, we obtain the first cumulant, which is just the expectation. But here, if j is anything higher, then we get actually the j cumulant of S0 plus. Okay, so this formula is very classical. If you remember, or if you've read about stochastic analysis, this formula follows immediately from the Cameron-Martin theorem and the definition of the Hermite polynomials. So let's take a look here. The definition, one way to define the Hermite polynomials is through their generating function. So e to the delta B0t. Here I read B0t, but I could put x instead of the Brandon motion. The generating function is e to the delta B0t minus delta squared t over 2. And that's equal to the sum of these Hermite polynomials evaluated at B0t times delta to the n divided by n factorial. So now, on the other hand, if you look at this guy, the left side here, that's exactly the Cameron-Martin factor. If you want to find the Radon-Nikodym derivative of a Brownian motion with a drift delta times s with respect to just a Brownian motion. Okay, so if I somewhat symbolically here denote f, a nice function of the path up to time t, and I multiply by this factor, take the expectation, that's the same as taking the expectation of f with respect to a shifted Brownian motion, where we've added a shift delta times s, and this shift only acts between 0 and t. Remember, because whenever we talk about B0s, we're talking about a two-sided Brownian motion, but when t is positive and we use the Cameron-Martin formula, we're only applying stochastic analysis to positive times, because the Brownian motion for negative times is just completely independent, so it doesn't see whatever we do. Okay. So now, if we take the left side and expand it using that generating function, and then differentiate both sides and set delta equal to 0, you easily obtain this, this formula here, this derivative formula. So a result, let me just spend 1 second on this, just making sure that everyone understands what's going on. Does this make sense? Okay, so we apply this to f being our partition function, which is a function of b0. And so as a result of this, applying this, this integration by parts formula, we have written expectation of log of z bar to the k. Of course, we could write an exact expression, but I don't think it really helps. I think qualitatively what's important is that we've written expectation of log of z bar to the k as a sum of products of expectations of the form log of z bar to the a times, this should be just log of, this could be, log of z bar to the a times the product I equal 1 to b of some cumulants of SCO plus with respect to the quench measure. And on the other hand, this is equal to a sum of products of this form log of z bar to the AB times some Hermite polynomials. Our problem, the reason why we're not happy with this formula is that the Hermite polynomials, if we Cauchy-Schwarz or Holder here, they are too big. Now the hope is maybe these guys, it's easier to see that they're not too big and that the homogeneity has been restored. So now you could try to actually estimate these higher cumulants of SCO plus. We're able to estimate the first cumulant, right? We were able to estimate expectation of SCO plus, but I don't know exactly how to estimate directly these higher order cumulants. You can compute their expectations, but computing their products or higher moments, I don't know. I don't know that this is of any very strong interest, but I just don't know how to do it. Instead, we're going to try to work these two formulas against each other. Okay. Our problem is that here t is too big. On the other hand, here things look good, but we don't know. T seems to have disappeared, or at least it's become implicit, so it's not as obvious that things are bad. But we don't know how to estimate the cumulants directly. But now let's dream a bit, and let's imagine that t were actually smaller. Okay, so let's replace t by say tau, which is something smaller than t. Then if we reverse the integration by parts that we did before, or not reverse, if we repeat the integration by parts that we did before, replacing t by tau, where tau is now smaller than t, but this is still the partition function with parameters n and t, then we get basically the same result. We get that the expectation of log of zn to the a times the Hermite polynomial b tau evaluated at b0 tau is also equal to a sum of products of cumulants, of expectations of products of quenched cumulants, except that the cumulants are no longer the cumulants of SCO plus, they're the cumulants of the random variable SCO plus minimum with tau. Okay, this follows just by applying, if you go back to the application of Cameron-Martin, the Cameron-Martin theorem, instead of applying it to B0 here, we apply it to B0 tau, and then we use that this will be adding a drift, which is not S times the indicator function of S between 0 and t, it will be indicator function of S between 0 and tau. Okay, that's the reason why this is true. Okay, but now we think about what we're actually trying to prove. Ultimately, we believe that S0 plus, or at least its expectation, is of order n to the 2/3. Okay, so really S0 plus most of the time should be no bigger than n to the 2/3. So when we look at the minimum of S0 plus and tau, we should be able, without very much cost, to change this tau here to anything that is slightly bigger than n to the 2/3, right? Because since S0 plus is already very likely to be less than n to the 2/3, if we replace the random variable SCO plus with SCO plus, the minimum of SCO plus and tau, where tau is something that SCO plus barely attains most of the time, we shouldn't have changed very much. But this is very good for us if we think about this second expression, because that would allow us to change this t here to a tau that is smaller. And if we change this t to a tau that is as small as what we believe and S0 to be, if we change it to n to the 2/3, then we get n to the 2/3 times the 1/2 coming from the fact that we're looking at Brownian motion. And then the homogeneity is restored. Then it seems like the induction is going to work. Okay. So more precisely, how do we implement this idea? If we knew a priori that S0 plus is much smaller than tau, then when we compute these quench cumulants of S0 plus and compare them to the quench cumulant of S0 plus minimum with tau, the minimum of S0 plus and tau, that difference should be very small because S0 plus is never going to be very much bigger than tau anyway. And well, if that's true, then by this integration by parts formula, it means that all these big terms that we had trouble with, all these terms that had this B0t, we can replace them with terms where t is replaced with tau. And then tau is now smaller, so we've made some gain. Okay? So, in fact, this is what we do. What we show is that we show that if we know a priori through some means that the expectation of S0 plus to the k is much smaller than tau to the k, then the expectation of log of z bar to the k is equal to the same sum that we had before, that we don't really care exactly what it looks like, as long as it's a sum of products of expectations of this form, and the ab and b sub b are such that a to the b is always strictly less than k. But now the Hermite polynomials are evaluated at b0 tau, so they're smaller. Okay, so this is saying, suppose you know that S0 is at most tau, then you know that log of z bar is at most tau to the k over 2, essentially. Suppose you already have a good bound for log of z bar to the L, for L strictly less than k, and you also know that S0 plus to the k is at most tau, then you get this improved bound for, or you get this bound for log of z bar to the k. So symbolically, we could represent this as follows. Suppose you know that expectation of S0 plus is at most n to the xi. Okay, so this xi is usually what physicists or people like to use for this exponent. It's called the fluctuation exponent. Then our method says essentially, so the first should be interpreted rigorously in terms of moments. Then our method says that also in terms of moments, log of z bar is at most n to the xi over 2. Okay, so if so recall that we already have a version of this in the case p is equal to 2 for the second moment. It says that we can bound the second moment of log z bar in terms of the first moment of S0 plus. So here I'm saying this is true for higher moments. We can bound, if you know something about the first moment or the kth moment of S0 plus, then you can say something about the 2kth moment of log of z bar. And again, symbolically, if we write log of z bar is n to the chi, then expectation of S0 plus is n to the xi. And what we just did gives us chi is less than xi over 2. Okay, that's just symbolic. This is sometimes called a scaling relation. Okay, I went a bit slower than I expected. So let's talk about, okay, so this tells you if you know something about S0 plus, you can know something about log of z bar, but now we still need to know something about S0 plus. Right? And that is actually something that really is the core of the coupling method. Before, what I showed you last time was, yesterday was using this inequality, but actually the coupling method is more powerful. It can give you bounds on S0 plus, and that's how it was implemented originally in many of these papers that I've mentioned. And the observation is simply that the partition function itself is a cumulant generating function for S0 because theta times S0 appears linearly in the Hamiltonian. So if you want upper bounds for the tails, well, just use this fact. Use the fact that you know that that log z is a cumulant generating function. So you just use what is it called? The Chernoff bound, the probability that S0 plus is bigger than u. We can bound this in terms of a ratio of partition functions, because the log partition function is a cumulant generating function for S0. So by changing the parameter lambda here, we can obtain a bound for S0 plus. Now, let's massage this expression somewhat by centering, by bringing ourselves back to the log partition functions and centering. So let's write the log partition functions. Let's center. And the cost of centering is we have this extra factor here, e to the expectation log of z minus expectation of log of z lambda minus expectation log of z theta. But this difference of expectations we saw last time, we saw yesterday, it is quadratic. It's lambda minus theta squared times n, provided we're in this region, n psi 1 theta minus t n to the 2/3. Okay. Now, what does this mean? So we're trying to bound S0 plus. We're trying to say, what is the probability that this is bigger than u? So we had better make sure that this is at least of the order of the remaining two arguments of these exponentials. So the argument in the final exponential is lambda minus theta squared times n. Now let's symbolically write log of z bar is n to the chi. Okay. Now matching powers in the argument of the exponential, we find that n to the chi should be comparable at least to lambda minus theta squared times n, that is this error between the expectations. And on the other hand, if we set u to be n to the xi, so that's the typical size of S0 plus, then lambda minus theta times u should also match lambda minus theta squared times n. It should also match this difference of expectations. So if we solve this little system, we find that lambda minus theta is going to be n to the xi minus 1. Remember, xi is this power that we expect S0 to be. Setting everything equal to each other, we find that this argument gives us that 2 xi is less than chi plus 1. Okay, so this Chernoff argument should tell us that 2 xi is less than or equal to chi plus 1. So this is somewhat symbolic, but this is what we expect would come out of this generating of this Chernoff argument. But we already have another relation between chi and xi, right? We already showed using this moment argument that chi is less than xi over 2. But if you know that 2 chi is less than 2 xi is less than chi plus 1 and chi is less than xi over 2, then you can find that chi is less than 1/3 and xi is less than 2/3. And those are the bounds that we wanted. In fact, if you know the rigorous version of this, what we prove with Nowak is that the kth power of log z is bounded by tau to the k over 2 if expectation of S0 plus to the k is bounded by tau to the k, and that the 2 kth powers of S0 plus is bounded by n to the k plus epsilon times expectation of log of z bar to the k. Symbolically, you can write it as these two inequalities above. And because we have these two inequalities, now what you can think of is just iterating. You can start with some initial bound. So we have some initial bound for log of z bar squared, and then some bound for the higher moments. And you use this bound for the higher moments to get a better bound for S0. From this better bound for S0, you can go back to the first equation and get a better bound for log of z bar. Then you keep iterating this, and the fixed point is this. Okay, so that's how you get bounds for the higher moments. Okay, so I didn't quite have time to cover everything I wanted to cover, but let me stop here to ask whether this makes sense. Okay, so there's a lot of stuff that is left unsaid here, but I should I'll just continue a little bit because I think it might address the question that was asked by somebody. Elnor Emra, yeah, it will. So there is a different approach. So remember, we started with this complicated higher order formula for the cumulants. There is a different approach that appeared recently. I'm going to call it the Rains EJS for Emra, Janjigian, Sepalainen identity. And this identity allows us to clean up a bit. It makes it possible to clean up a bit the work that we did with Nowak. So this is an identity that Rains found in the context of last passage percolation with exponential weights. But the interesting thing is that recently Emra, Janjigian, and Sepalainen gave a proof of this identity that shows that the only thing you need to prove it, or at least in the setting that interests us, is just stationarity. So in particular, you can adapt it to this O'Connell-Your setting, and you can use it to find nicer, I might have to say nicer, recurrences for the central moments than what we had with NOAC. So let me quickly just mention this because I think it's important to acknowledge that this exists. So it's a new preprint from May, and it uses also something called a non-equilibrium partition function, which will play a bigger role in the final lecture. So let's do the following modification to a partition function, which will seem a bit bizarre at first. Let's introduce two parameters instead of the one parameter theta. And one parameter is going to affect S for negative S0, and the other parameter is going to kick in when S0 becomes positive. So we have these parameters lambda and theta. So then we have this somewhat mysterious identity. So that's the Rain's EJS identity. That's how I'm going to call it. In our case, it looks as follows. Again, they were working in geometric, in the last passage, percolation with exponential or geometric weights. Anyway, but their realization is that the proof really just relies on stationarity, so we can easily do it for O'Connell-Your as well. So we have this identity for not quite the generating function, because there's a relation between the parameters lambda theta and the parameters lambda theta that appear in this modified partition function. And the point is that we can compute this exactly. Even though it's a non-equilibrium quantity, it can be computed precisely, exactly. So here phi is some function of the parameters. And then what is nice about this is that, and this is also, it should be credited to, Emra, Janjigian, Sepalainen. In the introduction, they noticed that this actually gives you not a recurrence relation, a generating function for central moments. Because if we multiply this expectation by this quantity e to the lambda minus theta, and now the log partition function with the two parameters being the same, this is just the log partition function we've been considering so far, it actually gives you, after expanding the exponential, it actually gives you a nice expression that is ripe for differentiation. If we differentiate this expression with respect to lambda and set lambda equal to theta, we get a different recurrence relation for the moments. And this recurrence relation can also be rewritten in terms of Hermite polynomials, and that allows you to really clean up some of the work that we did with NOAC using similar ideas. Their motivation for studying this was not this. They're actually looking at the probability that they use this to get bounds for S0 plus. But I think this is a very promising direction, and I think that there's the question: what did I mean with P or something? What did I mean is what I meant is just this. I just mean that this new work of you, Elnor, sorry, I don't think we've ever met, but of Emra, Janjigian, and Sepalainen, it allows you to study higher moments, with in a very nice way, in a very easy way. I mean, not easy, because you need to realize that you have this this identity. But once you have it, then you can get started and also study higher moments. Okay, so there's a lot more to say, but I guess for today let's leave it here. And then in my last lecture, I'll talk about something slightly different, a different approach, still in the O'Connell-Your setting, but a more stochastic analysis-based approach. Thanks a lot for listening.
Thank you, Philippe. Yuting, questions?
Questions, yes. So, so I'll start first.
Yeah. Okay.
So, so what is your what is the relation between these higher moments and the Tracy Whedon GUE picture? How are they related, or do you think